So we will start with easing into concepts. Basically, as you know, these concepts are one of the big four features of C++, along with ranges, modules, and coroutines. It's my favorite C++ 20 feature so far. I personally felt that the concepts are one of the things that were missing in C++ for a long time. But now we have the concepts. So now today we will discuss about it. The table of contents of my talk are: first, we will discuss about the overview of concepts, what concepts are. Then we will discuss about the concepts in the standard library. What are the concepts, predefined concepts that are available to us. Next, we will define our own concepts. It is further divided into subsections, and this will cover the bulk of my talk. Again, we will see those sections later. Fourth is real life usage. Again, I can give you the talk, but it will be, you can say, much beneficial to see some real life usage, how we can use it in a real life code base. Then we will conclude our topic. So let's start with overview of concept. Now, first thing we will discuss about what are the problem with templates. Here I have defined a simple add function that takes two parameters, a and b of type t, and returns the addition of those. But as you know, the templates are like the word star of C++. You can pass literally anything, and sometimes it can produce unexpected result also. Like here we can pass a pointer or even a boolean values, or sometimes it can give a long cryptic error messages. You know, the page long error messages of the problem with templates that are due to mainly templates. Or it also increases compile time. I know some people don't think about compile time too much, but I have seen some people that do, and sometimes they even write 3 to 5 functions instead of just defining a template. And here in the screen, you are seeing one of the long list of error messages. Basically, it arises due to this code snippet. Here I have a list of integers named id, and I am basically passing this list for onto the standard sort. And this is the error message that you will go. You can say it shows all the internal details that a user didn't want to know, and it didn't even say what happened wrong. I can even explain the why it is happened, but it will be better for the father of STL standard library, Alex Stefanov. So basically, here's a clip from a talk from the Alex Stefanov and Paramjit Oberoi. They will discuss why this happened.
So we have a whole bunch of concepts that we've used in all of our code, and these are all defined to type name. And it's just documentation today. Maybe at some point there will be a way in the language to express this. Today,
in 2 years.
So here is the definition of the sort function from the standard library. It requires a random iterator, random IT of type random access iterator. But when we look at the definition of random access iterator, it just defined to the type name. So it's just a name requirement. It didn't check anything like we are passing the right thing or not. And if you know all the, you can say, all the name requirements like input iterator, integral, forward iterator, bidirectional, they are just defined in the type names. So again, here the concepts come to the rescue. Again, I can explain you, but it will be better for the father of C++, Bjarne, to define the concepts.
And the thing we were working on is it becomes a bunch of constant expressions. It becomes a bunch of Boolean expressions. Does this type have this property? Does the argument type has this property? as the combination of types we get as arguments got this property. It's all predicates, it's all Boolean algebra. There's nothing about scopes, nothing about objects, nothing about indirect jump tables. It's all Boolean expressions.
So here, what Byan said that basically we are checking that the type have certain properties, and based on those properties, we are constraining a template. If the template parameter satisfy a certain property, then only this add function will be called. So basically, we have the add method here, and below the template head, we are constraining the template to accept only the type T which are addable or which satisfy the property addable. So here the requires is a C++20 keyword that checks whether a certain template parameter has this property. So again, we are constraining a template. So now we will look at a few of these certain concepts in the standard library that we get predefined. First is the integral. Here I have defined the add function again, but here in the fourth line below the template head, I'm requiring this add function to have a certain type T that is an integral type or which satisfies the concept integral. Basically, integral is satisfied when the type is either an short, int, long, and also it accepts Boolean and character values, including the white character, because of the internal implementations. But we will look at how to solve that. In main function, when I try to call the add function with some integer values, it will call fine. And again, in the second line, in the main function, I'm calling it with the some short values. It will compile fine. But when I will try to call it with some floating point values, it will produce an error. Next is the floating point. Now, floating point is similar to the integral type, but it checks whether the type T is a floating point type. That is whether it is of float, double, or long double. Here I have the same add function that I defined previously, and instead of requiring the integral, it checks whether the type is a floating point type. And now in the main function, I'm calling the add with some double values or floating point values. So basically it will compile fine. But when I will call it with some integral values or integer values, it will produce an error. Now I know due to some time constraint, I have to, you can say, I have to reduce this section. So here are some of the concepts in the standard library. You can go to CPP reference and check these. But due to covering some of the more important sections, I have to reduce this section. So in the core, basically the concepts in standard library are divided into 4 types. First one is the core language concepts. Here, some of the concepts are like integral, signed integral, unsigned integral, floating point, swappable, constructible from, default constructible, etc. In comparison concepts, we have the concept that are used for comparison, like the equality comparable, whether the type is in equality comparable or not, and also the totally ordered. In the object concept, we have the concepts on the object or constraint on objects, whether a particular object is movable, copyable, is regular or semi-regular. And in the callable concepts, it constrains a particular function or stood function, whether it's invocable, it's regular invocable, or whether it's an predicate. So again, you can go to simply CPP reference and check those concepts. Now, here comes the most important topic in the presentation: how to write our own concepts. This is divided into further sections. The first one, we will see how to write concepts with the functions. Second, we will we will see how to use concepts with the classes. Then the require expression. After that, we will see how to combine different concepts. And last, we will see the concept subsumption rules. So let's start with the concepts with functions. First, we will define here. You can see on the fourth line, I have defined a concept. Basically, concept is a C+20 keyword that is used to define a concept. I have defined a concept number that requires the type name t to satisfy either an integral or a floating point. That it requires the type t to be either an integer type or the floating point type. Basically using the predefined concepts are one of the easiest way to define our own concepts. We will see different methods later on. But here in the you can say in the below above the add function, we have defined a template head, and the template head I am basically requiring the type name t to basically satisfy the concept number. That t should either be an integral or a floating point type. So we can now call it either with the integral values or floating point values, as I have as shown in the right snippet. But when we will try to call it with one integral values and other floating point values, it will produce an error because it requires the the types should be of same type. Second, before this, as you know, in C++, we have multiple ways to achieve a similar or desired solution. So we have a different, you can say, ways to constrain a function or use concepts. So we will quickly just go through them. Second is the requires clause or add a constraint. Basically, we will not define a concept. Instead, we will list out all the constraints that we want from our function below the template head or in the requires clause only. That's why the name ad hoc constraint. So basically in the fourth line, you can see that below the template head, it requires either the t should be satisfy the integral type or the floating point type. Again, we are not defining concept. We are, you can say, just defining it at function place, like a lambda that we define at the function call. But please note that it can be used in one place only, and when you want to use the template at multiple places, please define the concept. Third one is the trailing requires. Again, it is similar to the requires clause, but the requires clause come after the function signature. That is after these CV values, const or volatile values, CV definition basically. So here I have again defined a concept integral concept number that the t should either be an integral or floating point type, and I am basically constraining the auto. And after the function definition, you will see that it requires the t to satisfy the number constraint. Again, it is similar to the requires clause. Next is the constraint template. Here, instead of the requires clause, we will basically replace the type name with the concept name. So again, I have defined the concept number. It's the same as in the previous slides. And in the add function, in the template head, I'm basically, instead of the type name, I'm specifying the name of the concept. That is the number. That t should be of number type or satisfy the number. Again, but it didn't, you can say, support a combination of concepts that we can list only one concept only. Fifth one and the last one is abbreviated template. Here we don't have requires color, even we don't have the template head. As you can see in the add function, in the parameter we can list we can directly, you can say, constrain the types A and B, that A and B should be of number auto. Basically, we are constraining the auto itself. That whether that the auto should be of type number. Again, this doesn't support the combination of concepts. We have gone through them quickly, but but uh, but now the question arises: are there any differences between these? So I basically called the add function with two integral values, and I basically look at the template instantiation on the CPP inside, and the add requires clause basically specialized to this template instantiation. So basically, the template parameters are an integer, or it requires parameter values. The same is for the ad hoc requires. Again, the template initialization are the same. Next, we have the add constraint types. Again, the 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 template initialization is the same, as it also requires the int. So basically, it happens at the compile time, and the linker will not even see your constraint. So it happens before the initial, you can say, template instantiation also. And on the fourth, we have the add trailing requires. Basically, it has the same template instantiation, but after the function declaration or definition, we have the requires number int. Basically, I checked the standards, and it didn't say that the linker will see the, you can say, your constraint. But again, it could be due to some of the bug. But the main point here that all the template instantiation you will get will be same, or all your templates will of the same type, whether you use ad hoc requires clause, constraint, or the trailing requires clause. But when I check the template instantiation of the abbreviate function, it specialized with this. Basically, it requires two template parameters instead of one. It requires of type int, comma int. That it requires two integral values. Now, some of you might say, what is the difference? But you have to be careful. Like here, I have the add abbreviate, the same add function that we have looked in the abbreviate template example. We have the two types, A and B, and we are basically constraining them to be of number type only. And when I try to call the add abbreviate with the integral and a floating point value, basically it will compile fine, and it will, you can say, it will specialize to this template instantiation for specialization. So the parameter that you pass to the abbreviate template function can be of different types also, although it depends on your application whether you require it or not, but you have to be careful about it. So now the question arises, how to choose between all these choices? So this can be simplified by asking some basically two questions. First, if you want to reuse the constraint or the concept, that you, that if you want to reuse the constraint, then you have to basically define the constraint or concept. But if you don't want to reuse the concept or constraint and have a simple basically requirement, then you can use the ad hoc or the trailing ad hoc. Again, it doesn't matter. Basically, the template instantiation will all be the same. But if you want to use the constraint again, or you have a complex requirement that you don't want to define at the function, then you can use either requires clause, trailing requires, constraint template, or the abbreviate template. But basically, you have to be careful about it, about the abbreviate template. Next is the constraint auto. Basically, the add abbreviate that we see is an example of constraint auto. Basically, we are constraining the auto to be, you can say, to accept the types, that to accept the values that satisfy the number concept. But here in the add function, I'm constraining the parameters a and b as well as the return type. That the return type of addition of a plus b should also be of number auto. Again, because in the you can say due to when we will look later, we basically the when we look later when we have some custom types that could you can say return some proxy types or other values. And in the main function, I am defining two integer values a and b. And in if context per, I am checking at compile time whether the type of a, that is the integral type, supports the or you can satisfy the number concept or not. If it satisfies, then the body of this if context per will compile and get executed. Otherwise, it will not be compiled. So basically, I'm checking at compile time. And in the body of if context per, I am defining a variable auto of type number. Basically, I'm constraining the auto to you can say to to initialize the result with the number value only. And I am so basically the add function will return the value and the result will hold that value. It could be you can say useful in situations like we have we have a we have a C++ application that interact with the Java applications via bindings, and the user you can say upload some of the documents, and we want to check whether the document is of valid type or not. So we can check again at the compile time. Next is the concept with classes. How to use the concept with classes. Again, this is similar to a function, but instead here we will define the constraint on the class template. So basically we have the ad hoc requires. I have a class bounded number that will basically wrap a number and keep it within a certain bounds. It will also check for overflow, and if overflow happens, it will again wrap it into a certain bounds that we have defined. Here I have in below the template head, I have required that the t should be of integral or floating point type, and in the private the num is of t type, that is it is of number type. So basically I'm constraining the class level template. Next is the requires clause. This one is similar to the previous example, but here we we have the you can say we first define the number concept. I'm not defining it here because we have seen it multiple places, but you have to define the number concept, and then we will requiring the t type to satisfy the number concept. Again, it is good for places when you need the concept to be used at multiple places. Next is the constraint template. This one is also similar, but we are constraining the template head, or you can say the template itself, the template parameter. So again in the type name, instead of type name, we have the number or the concept name, and the last is the trailing requires. This one is a you can say different or special, as in the previous examples we are constraining the class level template, but here we have class level template and we are putting constraint on function. Basically we have the template type name t, so basically it is a unconstrained template, but we are defining we are requiring, or you can say we are defining the constraint on our divide function, that the divide function will be called when this t type is of integral type. So again we are constraining the function, but not the template parameter itself. But it has its own advantages, like this one. Here I have two divide methods. The first divide method will be called when the type t is of integral type, and the second divide method will be called when the type T is of floating point values. So basically, I want I want I want different block of code to be executed or different method to be called when the T is of integral and floating point types. So basically in assembly, there is a, you can say, there is a lot more, you can say there is a lot more difference in the execution time in the integral type division and the floating point division. So basically this is used for, so basically I am constraining for optimization reason only. So for the first, so here the first divide method will be called when the T is of integral type, and the second divide method requires the T of floating point values. So when I call the add method, if the T or the value that I provide is of integral type, then the first method will be called. Otherwise, the second method will be called. Now comes the require expression. Here we will define the requirement of expressions. Before we are constraining the types, but here we are constraining the types based on expressions, whether the certain expressions are valid or not. First, we have the requirements on operation. So I have a concept addable, and I basically requiring this addable type to require basically two variables of type T, A and B, and these two type should be addable, or you can say there is a operator plus defined for them. So basically we are constraining the operations, or you can say the expressions. Now instead of, you can say, saying the my my parameter should be of number type, we are constraining on the type that there should be addition operator defined for them. Now it is, you can say, it is much more useful, as you can say, as before our constraint only, our add function only accepts number types, but now we accept all the types that have a operator plus basically defined for them. So basically I have the add function instead of the number template. It is requiring the type name T to satisfy the addable, that there should be an add operation defined for them. Next is the requirement on interface. Now instead of operation, we are requiring the A of type T to have a method square. So the A should have a square method defined, and please note that the square method should be public. So basically we are defining the constraint on interface itself. Also, next I have the concept power, and it requires the type name T to have a method power that accepts an integral value, exp or exponent. Again, this one is similar to the previous one, the square, but it requires the method to accept an integral values. Next one is the nested requirements. It is same to the previous example, but here we are constraining multiple, you can say we are listing our multiple constraint in a simple requires expression, that the exponent checks whether the A object of type T has a method square as well as a cube. Next, we have checked the whether there is a function and it accepts certain values, but we didn't specify anything about the return type, whether the return type should be something that we, you can say, we are constraining. So basically now we are constraining on the return type. Basically now we have the concept square. It requires a T object of type capital T. Now the T object should have a square function or square method, and it also has a it should be and its return type should be convertible. Basically, we constrain the return types using two concepts. First one is the convertible, and second one is the same as. The convertible checks whether the type that is you can say returned by square can be converted to t that is passed that the type which is passed to our parameter. Basically, the type can be can be statically casted to the type that we mentioned or not. Whereas the same as requires that the both of the type should be same. So here we in the square, I'm requiring that the t should have a square method, and also the return type of t should be convertible to integer values. Again, the type could be anything that you require. Next is the compound requirement or requirement on return type. So here I have the concept addable from before. It requires two parameters A and B, and it requires there should be a operator plus defined for them. But now we are actually listing two more constraints that the operator plus should be no except, that it shouldn't throw any exception. Also the return type should be the same as of type t that the parameter we have passed. Now we will move towards the concept overloading. How to overload different concepts. Here I have an, let's say we have a software as application or SaaS. Basically basically we have some application, and on application there are two types of user. First one is a free user or free account, and second user that have a paid account or basically paid users. So basically now I am constraining my method based on whether they are free account or paid account, because I want different methods to be called depend on the type of the account. So here I have the first billing method, and it requires the t to satisfy the is free account constraint, whether the type is free account or not. If it is free account, then the first billing method will be called. Otherwise, the unconstrained type we basically have only two types. As we all know that we basically have two types only, the free account and paid account. So the unconstrained account will be called. So basically we are constraining whether a certain type has this property or not. Now you can combine different concepts to form new concepts, as I have seen in the previous example. That here that the number concept, we basically combine the stored integral and the stored floating point concept. That the number should either be an integral type or a floating point type. But you can also combine different Boolean literals, Boolean expressions, type traits, and also require expressions to form different concepts. And also you can use the negation or the note. So again, we have the billing method. But now, say we want additional functionality, like there should be discount code, and when the user type in the discount code, he will get some of the, you can say, benefits, or you can say the sum of, you can say, the total amount should the sum of the discount. So now we have two billing methods. The first one requires that the t should be of free account or satisfy the free account, and now and next we have the billing method, second billing, that requires the t should satisfy the free account as well as discount code. So when we call our billing method with type with certain type, if it satisfy both the constraint, then the second billing method will be called. Otherwise, the first billing method will be called. This is due to the concept subsumption rules that the compiler will choose the most constraint, or you can say the most constraint overload all of the. Now I could go on and you can say my initial plan was to go on and include more of examples, but again due to type constraint I have to show some real world usage. So I am, you can say, reducing this combining concept section, and as well as I'm completely removing the concept subsumption rules. But again, you can you can I will provide a link of the article from India's verdict that will explain it better or well. Now we will see some real life usage. Now basically this is the intent that I want. I want my add function to be called with n parameter, or you can say n types of arguments. I don't care about the type. It could be of integral or floating point, but I don't want my add function to, to the parameter of my add function to be called with different parameters. So basically, we are we have to constrain the template pack, or the constraint. We have to basically we so basically we have to constrain a template pack or variadic template. Now again, this could be achieved in C+17 also. So first we will look at the C++17 example. How we can constrain a variadic template in C++17. First of all, we don't have any helper, or you can say type traits to be used on a variadic template. So what we will do, first we have to define some of the type traits. So basically, now I am in the fourth line, I am defining a type trait r same v. Basically what it does, it basically calls the stood conjunction on the my is same type trait, whether the first value or the type of the first value is same as the rest of the values. So basically I'm checking whether the type of the first value is equal to the type of the all values. That is the all the types in my first in my variadic template or template pack are of the same type. Next, in the last line, I'm defining another helper function, uh, first arg. Basically, what it does is it it gives me the type of the first argument, because I want it to be, you can say, I want it for the return type. So what it basically does, it defined a structure first arg, and using the first arg we are obtaining the type of the first argument that is passed. Now the real body looks like this. We have the add function, and above the add function we have the stood enable if t, and stood enable if t requires two parameters. First is the boolean expression on which we are constraining, or you can say we are checking, and the second is the return type that we want. So basically we are checking that the template pack or variadic template are of the same type, and if they are of the same type, then the first arg or you can say the type of the first argument will be the return type of the add function. But if the condition is false, that the types in the template pack are of different types, so then this enable t will be false, and basically this add function will not be here, or it will not be even instantiated. Again, this is, you can say, one of the code that didn't want to use. Although sometimes we have to use it, but we certainly didn't want to use it. It's so much lengthy, it's so much cryptic actually. But this could same be achieved in less code in C+20. Basically, now I want the RSMV concept from the previous example because I am using it to check the requirements on my template pack. So basically, again I can define it as concept, but for just for the sake of simplicity, I'm defining as const x per bool or a boolean expression. So now I'm constraining my add function that it should require the template args or the variadic template to be of the same type. You can take a look at it for a few minutes. It's so much simpler and concise than the previous example. Basically, I'm checking whether the types in the template pack are of the same type. And it is checked by my RSMV that we have seen in the previous example. But we can improve this template pack. First, that it can the first improvement could be that it should be called with more than one argument. Basically, in the template pack, we can call it this add function with one argument only. We don't want that actually, and certainly you shouldn't also want this to happen. Next, I want my arg to have the operator plus. Previously, we are checking whether all the types are of the same type, but we are not checking whether they have the operator plus defined for them. So the previous one could still give an error. Next, I also want my operator plus to be of no except, that it shouldn't throw exception. As my previous add is no except, and I certainly don't want to, you can say, wrap it in a try catch block. And the fourth, that the return type of the addition should be same as the arg or the type of the argument passed. So you can imagine how to, you can say, constrain template pack in C++17. But we will not go here, and we will now be showing how we can achieve the same in C+20. Now, basically, the first two lines are of this are the similar to the previous one example. That my add function is accepting a template pack or variadic template, and it requires my argument or variadic template to be of the same type. And in the third line, we are requiring that the size of the args should be greater than 1, that it should contain more than one element. And in the fourth line, we are using a requires expression. And the requires expression, the first is that it should support operator plus, or you can say the addition operator. Basically, I'm using the template expansion here, the template expansion syntax. And the second line, I'm checking that the addition of all these arguments should be no except. And in the third line, in the requires expression, I'm checking that the return type of this should be same as the first type. And we are checking it with the help of the first argv that we have defined in the previous slides. So now my add method checks for all these. Now this is the code that I could use it in a real life example, and it's basically foolproof. But again, we can improve, or you can say make it as something concise. as we can check all the three requirements in a single line only in the requires expression. Again, it depends on you, but both of the requires expression are, you can say, are similar, or you can say they check the same requirements. Again, you can have a look at this for a few minutes. Basically, I have prepared a lot more examples for this. My second example could be a wrapper that basically behaves behaves like the parameter that is passed to it. So basically, it behaves like a like its parameter. So if I, you can say, if I ask whether on the wrapper that it is whether it is default constructible, it will behave like the object that is passed to it or its content. So if the object is of, you can say, default constructible, then it will return true for the type rate default constructible. Otherwise, it will behave it will return false. So basically, it will be lot like form wrapper. But again, due to time constraint, I have to remove that example. But the slides that I will share will have it. So basically, you can take a look at it later in the slides that I will share. Now we will conclude this topic. First is better type checking. That the concepts support better type checking. Now again, I have the concept number, but here I'm improving that concept from the previous one that we have seen. Now my number should either be of integral or floating point type, but it shouldn't be of Boolean character or any wide character. So basically, I'm combining the concept to form a number. It should either be an integral or floating point type, but it should not be same as of bool, char, and other wide character. So again, this is the example that I could use in a real life scenario, my concept number. So concept gives us better type checking. Now I have some snippet. I have a process method that accepts a business object, but certainly I didn't know what this business object is, or what is required to be called a business object. So it is just a normal code, but with concepts we can write self-documenting code. Okay, so now we are requiring the business object to be a regular type. If you don't know of regular type or semi-regular, you should certainly watch the one of the videos from the Sean parents. He described it really well actually. So we are requiring that the business object should be of regular type. And in the second requirement, I'm requiring that the business object should be derived from a certain base class. And in the third requirement, I'm saying that my business object should be movable. So again, we can get a clue that we might be want to, you can say, move the business object using the standard move or should move. And in the fourth requirement, I'm saying I'm requiring that this that this business object should have a certain method. So again, you can see it turns a normal code into self-documenting code. Fourth one. Now this is similar to the example that I've shown. Basically, that in the you can say during the initial slides that I'm initializing some list here. I'm now calling it with ranges instead of the iterators. Now ranges supports the concept. So now we will get better error messages, and it actually shows that my list didn't satisfy the random access iterator. Next one is reduced compile times. Again, I could tell you, but I would summon Pyarne.
Code using concepts compile faster than code using workarounds. Eric Niebler reported 2 weeks ago that the ranges TS that exist in two versions, enable if and with concepts, compile 25% faster with concepts. Expressing things directly is better than representing things indirectly. And we're winning on all counts with concepts over the previous workarounds.
So as you have seen, using concepts, the compiler can know in advance that this is the type that I am expecting. So it could, you can say, use better optimizations and also make the code to compile faster. So again, I say that there is not a single reason not to use concept. If you have a better reason not to use concepts, I'm here. Please change my mind. And also, if you have any question, please ask me.
Hey, hi Kashish, over here. Thanks for
Hello.
the session.
Yeah.
I have basically two things. One curious question, like the two things basically. So the first one being, so I understand that it has the 25% as he said, right? Improvements in the performance compile time. But does it have any implication on the the runtime at runtime? And this is first question. And the second one is like, if possible, after this session, if you can point us to like how concepts work internally, just to satisfy my curious mind, like how it internally works, what exactly compiler is doing to make that optimization. So it would be really great. Thanks.
Okay. As I have previously told, that they are compile time only. Even the, you can say, linker will not see your constraint. So basically, it didn't have even a single impact on the runtime. Your code will be as faster as it is with, you can say, it is with templates basically. There is nothing on the single, you can say, you can say, even a penny, you can say, even a
Okay.
even a penny effect on the runtime. And second, basically, let me go back a few slides. So basically, they are just, you can say, basically, in this I have also, you can say, defined some concept. Basically, the internal representation is in this struct only, that the compiler will try to initialize this struct or a structure, and will, if it initialize well, you can say, the argument supports that properties, it will, you can say, it the concept will be satisfied, otherwise it will be not. So basically, it's just like type rates. And I have also told that you can also combine type rates or Boolean expressions to form a new concept. So yeah, we can chat more about in the Discord, actually, internal details.
Sure. Thanks.